In this video, we're going to talk about section 11.2 slope fields. So slope fields give us a way of visualizing the family of functions that make up the general solution to a differential equation, as well as what a particular solution might look like. So I think the best way to understand what a slope field is to actually make one. So we're going to make a slope field here, and then what we'll do is we'll actually solve this differential equation, and then we'll put in a couple of different initial conditions to see what a couple of different particular solutions might look like. So what we're going to do here is we're going to look at our differential equation and understand that that derivative dy dx is the slope of a tangent line at some particular value. In this differential equation, it depends only on the y. So for example, if we look at the places where y is equal to 1, then the slope of the tangent line to a solution curve at each of those points is going to be 1. So for a slope field, we're going to draw just a little segment that's going to be a little part of a tangent line at those points where the y-coordinate is 1. And so I'm trying to make these look like they have a slope of about a 45-degree angle. Now at all the points where y is equal to 2, this is going to be then a little bit steeper because a slope of 2 is a little steeper than a slope of 1. Similarly, at y equals 3, they're going to be even steeper still, and pretty soon it gets kind of hard to distinguish them almost from a vertical line, but we aren't usually going to do too many points. Now, all along the x-axis, at all of these points, the slopes of the tangent lines are going to be 0 because the y-coordinates are 0. So I'm going to get just these little horizontal pieces of tangent lines. Once we dip down below the x-axis, now the slopes are going to become negatives. So all along the horizontal line, y equals -1, we're going to get slopes of tangent lines that are -1, and so they're going to be going down at a 45-degree angle. And then we go to y equals -2, so those are going to be steeper still. And then we'll do y equals -3, and we'll go even steeper still, and we get something that looks like that. So when you see this, remember, this is just kind of like giving you a flow. So as you look at those, it seems like they might be kind of, if you're starting with a point that's above the x-axis, they're going to look maybe kind of like an exponential growth curve. And if you're starting at a point that's below the x-axis, then you're going to get something that looks like maybe a negative exponential, something that was an exponential growth that got reflected over the x-axis. And if you should start on somewhere on the x-axis, you are going to just stay on the x-axis. So let's add another dimension. We're going to actually solve this. So these are, again, what we call separable differential equations. So to separate the variables, and we only have y on this one. And before I go on, let me just talk. Notice that because sometimes what we'll be asked to do is to start with a slope field, or maybe have a multiple choice of different slope fields and try to match them with a potential curve or a potential differential equation. And so you can see here that because our differential equation only has a y in it, that they do not change as you go from left to right. That is, all the slopes of the tangent lines here stay the same for the same value of y, which is kind of a clue that the differential equation has only a y in it. You can also see that they are all positive slopes when you're above the x-axis and all negative slopes when you're below the x-axis. And also notice that the places where we have horizontal tangent lines, those horizontal slopes, appear as a horizontal asymptote in our solution curve, and they're very distinctive. So back to solving our equation, our differential equation, I'm going to divide the y to the other side so that it can be next to the dy. At the same time, I'm going to multiply the dx to the other side. So at this point in time, I have separated the variables. Everything with a y in it times dy on one side, everything with an x in it, which there isn't anything, times dx on the other side. Then we're going to integrate both sides. The left side we're integrating with respect to y, and the right side we're integrating with respect to x. So on the left side, we're going to get the natural log of the absolute value of y, and on the right side, we're going to get an x. Now, you could think of each of these sides having a plus c, a constant of integration, but we're just going to lump them together, and we're always going to put them on the side of x, because remember, ultimately, we're going to try to solve for y. Now, this part next is going to be kind of strange. Now, this absolute value we're going to account for in a moment here. We're going to get out of the logarithm by exponentiating both sides. And so that's going to give us just a, I'm going to go to just a y, and I'll tell you what happened to that absolute value in just a moment. So on the other side, we're going to get e to the x plus c, but we're going to think of that as e to the x times e to the c, right? Because property of exponents, when you multiply two powers with the same base, you add their exponents. So we're going kind of in the other direction that we usually do with our properties of exponents. Now, e to the c is e raised to some unknown constant, because we haven't tried to solve for that yet. So that itself is just a constant. So we're going to call that just c e to the x. So it's some constant times e to the x. Now, let's go back and talk about that absolute value. When this had perhaps an absolute value to start with, if we drop the absolute value, that means that it could be equal to a positive or a negative value. Think for a minute, like if we had the absolute value of x is equal to 5, x could be either 5 or a negative 5. So our y that was in absolute values could be either equal to a positive or a negative times e to the x. Well, I don't need an absolute value for that because I haven't decided what that c is yet. It could be either positive or negative depending on what the initial condition is. So I don't have to say plus or minus because it can't, in the end, it can't be both. It can only be one or the other because it won't be a function if it's a plus and a minus both. So the takeaway is we can write that absolute value initially when we integrate that, but once we put in our c, like we have here, we no longer need that absolute value. Now, so what we see here is our general solution. It's an exponential growth function. Now, I'm going to do a couple different initial conditions. So suppose that our initial condition was, I don't want to use blue. So suppose our initial condition was 0, 1. That is, this is our differential equation, and it has to contain the point 0, 1. So if we go to 0, 1 on our graph, we can see now that it's got to follow the flow. So this is not like a connect the dots thing, but it's going to follow the flow but contain that point. So that means it's going to be an exponential growth curve. We could actually solve for our c in this case, because if we say 1 is equal to c e to the 0, that means c is going to be equal to 1. And so our particular solution is going to be 1 e to the x. Alternatively, if we said we had an initial condition that was 0, negative 1, then we would start with our general solution, the y equals c e to the x, and now we'll plug in 0 for y, or 0 for x, and negative 1 for y. And so in this case, we're going to get that c is negative 1, and our particular solution is going to be negative e to the x. So we recognize this, hopefully, as a point that's going to go through 0, negative 1. negative e to the x is our reflected growth curve, and you can see it's going to follow that flow of that slope field, and we're going to get that for our solution. We could even get that if our initial condition was 0, 0, then our general solution, y equals c e to the x, if we plugged in 0 for y and 0 for x, we would get that c is 0, which would make that equation be just y equals 0, which means it would just be that horizontal line, which you can hopefully see follows the suggestion from our slope field. Okay, let's try another one. So this time our differential equation is going to be dy dx equals 2x. So now we can see the slopes are going to depend only on the x-coordinate of the point. So when x is 0, that's going to be all along the y-axis, we're going to get 0. So we're going to get horizontal tangent lines all along the y-axis because all those points have x-coordinate 0. All along the vertical line x equals 1, we're going to get slopes of tangent lines that are positive 1, and so are going to go at a 45-degree angle up. When x is positive 2, we're going to get slopes that are positive 2 all along that vertical line. And when x is positive 3, we're getting even steeper, and it's getting kind of hard to distinguish, but when we get them all there, we'll be able to see the flow. When x is negative 1, we're going to go 45-degree angle at a negative slope, so we're going to get something that looks like that. And negative 2 is going to be steeper in the negative direction, and negative 3 will be even steeper still. So when we look at this slope field, we can kind of get a feel for the flow of that. You can kind of see what that's going to look like. If we separate our variables and try to solve this, there is no y, so we can just, now normally we would probably move the constant, we would leave the constant on the x side. We try to keep the y side as decluttered as possible, because ultimately what we're going to have to do is solve for y, because our solution to a differential equation is going to be that function y equals f of x. Once we have separated the variables, we are going to integrate both sides, the left side with respect to y and the right side with respect to x. And so we see we get y equals x squared plus c as our general solution, and that's kind of what it looks like when we look at that slope field. We know that y equals x squared is a parabola that opens up, and the plus c is just going to change where the y-intercept is, where that vertex is going to be. And when you look at that flow, it is very suggestive of parabolas. So again, if we say we have an initial condition, say of 0, 2, then when we plug in 2 for the y and 0 for the x, we are going to get that c is 2. And so our particular solution is going to be y equals x squared plus 2. And that would look like a parabola that opens up and has y-intercept 2. If we chose an initial condition of, say, 0, negative 1, then we would get that our c is negative 1, and the parabola is going to be y equals x squared minus 1, and that's going to look something like that. Going back to before we drew those, I meant to talk about this, and I skipped over it, kind of like we did on the earlier slope field. When you look at the characteristics of this, you see that they stay the same on each vertical line, and they change as you move across from left to right, and so they are changing with x only, and that's suggestive that it comes from a differential equation that has only x in it. You can see that the horizontal tangents appear all on the y-axis, And that also tells us that we're going to have the slope of the tangent line. The derivative will be 0 when x is equal to 0, which is also a way of maybe identifying, if we had a bunch to choose from, like in a multiple choice problem, which differential equation corresponds to our given slope field. Okay, let's try another one. Okay, now this one you can see the differential equation has both y's and x's in them. So what we can do now is we have to work at these points together. Now there are a few real important conditions here. When y is 0, this will be undefined. So normally what happens, like on an AP exam question, is when you get 0 over 0, which is what we would get at the origin, when the x-coordinate is 0 and the y-coordinate is 0, it will leave that blank. When the numerator is not 0, like say at the point 1 comma 0, so where our tangent line is going to have a slope of 1 over 0, that will be interpreted as a vertical line. So a vertical tangent at the point 1, 0. So we're going to get a vertical tangent here, and in fact all along the line y equals 0, which is the x-axis, except we'll skip the place at the origin where we had 0 over 0, and we will not put any tangent line at all there, because we'll just say it's undefined there. Okay? Now, if we go to a point, like say, where the y value now is positive 1, so then what we're going to get is negative x over 1. So when x is 0, we're going to get 0 over 1, which is 0. When x is positive 1, we're going to get a negative 1. When x is positive 2, we're going to get a negative 2. And when x is negative 3, we're going to get a negative 3, a really steep negative slope. Going to the left, when x is negative 1, we're going to get negative 1 over 1 is positive 1. When x is negative 2, we're going to get a positive 2. And when x is negative 3, we'll get a positive 3. And we're going to keep going this way. So let's look at what happens when y is 2. Again, when x is 0, we're going to get 0. In fact, all along the y-axis, except at the origin, we're going to get x to be 0. When x is positive 2 and y is 1, we're going to get a negative 2. And when x is a, oops, I did that wrong. When x is a positive 1 and y is negative 2, we're going to get a negative 1/2, which is a little flatter. And then we'll get our negative 1, and then we're going to get a negative 3/2, or negative, I'm not doing that right. Yeah, negative 3/2, so a little steeper still. Going in the negative direction, when x is negative 1, we're going to get a positive 1/2, which is a little flatter, then a positive 1, and then a positive 3/2. When x is a positive, let's see, now we're up at where y, let's do y equals 3. So when y is 3, if x is 0, we're still 0. When x is 1, we're 1/3, or negative 1/3. So that's even flatter still. Then we're going to get negative 2/3, and then a negative 1, which is about a 45-degree angle. Then going in the other direction, at negative 1, we'll get a 1/3. So that's going to be pretty flat. And then a 2/3 is not quite as flat. And 1 is going to be a 45-degree angle. Going into the negative direction, or when y is now, let's say, negative 1. So when x is negative 1, we're going to get negative of negative 1 is 1, over negative 1 will be a negative 1. Did I say that right? I better write that out. So a negative of negative 1 over negative 1 is going to be negative 1. So we're going to be right. Is that right? That doesn't look right. That's because x is positive 1. That's my goof up. So that's going to be the negative of 1 over negative 1, which is positive 1. That makes better sense. So that's fitting more with what's kind of looking like it's going to evolve into circles, I think. When x is 2, we're going to get negative 2 over negative 1 is positive 2. That's steeper still. When x is 3, we're going to get negative 3 over negative 1, which is positive 3. When x is negative 1, now we're going to get the negative 1. When x is negative 2, we're going to get negative 2. And when x is negative 3, we're going to get negative 3. Now we'll look at y being negative 2. And so this gets tedious in a hurry. So now when x is positive 1, we're going to get negative 1 over negative 2 is a positive 1/2. When x is positive 2, we're going to get negative 2 over 2 is 1. When x is negative 3, or positive 3, we're going to get a positive 3/2. And going in the other direction, when x is negative 1, we're going to get a 1/2. So let's see, that's a negative 1/2, I'm sorry. So that's going to be like there, and then a negative 1, and then a negative 3/2. When x is, we'll go now to y equals negative 3. So when x is positive 1, we're going to get a negative 1 over negative 3 is a positive 1/3, then a positive 2/3. Wait, I didn't do that right. Positive 1/3, positive 2/3, and a positive 1. In the other direction, negative of negative 1 is going to be positive 1 over negative 3, so a negative 1/3, then a negative 2/3, and then a negative 1. Okay, now here is something to note. Like we talked about, I did a better job on the first one. When you look at this, you can see as you look across horizontally, as the x values change, so do the slopes. So that would indicate that our differential equation is going to have an x in it, which it does. When you look vertically up and down, you can see that the slopes change as the y values change, which would indicate that it has a y in there as well. Now, with some distinguishing characteristics, because it has horizontal tangents on the y-axis, that's when x equals 0, we would expect to see that 0 in the numerator. And since we get vertical tangent lines when along the x-axis where y is 0, that is going to confirm that y is in the denominator, so that when y is 0, then we're going to get vertical tangents, undefined slopes. Okay, those are characteristics. Sometimes it helps also to notice that something like, in quadrant 1, all the slopes are negative, which means that when x is positive and y is positive, we're still going to get a negative slope. And that's kind of giving us a clue maybe on that negative sign there, because when x and y are positive, we're still going to get negative slopes. So those are all things to consider when we're trying to figure out how to match a slope field with a differential equation. Okay, let's see if we can actually solve this thing. I don't know if I can, let me erase some of this stuff to create some space. We're going to try to separate the variables here, and we're going to try to solve the differential equation, and then we'll put in some, I should say, when you look at this, it looks like solutions are going to be circles. But be careful. Remember that solutions to differential equations must be functions. So what we're going to see is that if we get an initial condition that has a positive y, we're going to get a semicircle, but only the top half. If we get an initial condition that's negative, we're going to get a semicircle that's only the bottom half. It cannot be the full circle, because that would not be a function. Okay, so just a word of caution. Let's see if we can solve this thing. So we're going to separate the variables. I'm going to multiply the y to the side of dy, and we're going to multiply the dx to the side of the x. And I would leave any other complicating factors, in this case the -1, I would leave it on the x side, because we want the y to be as pristine as we can. So we integrate both sides, so we're going to get a 1/2 y squared, and then we're going to get a negative 1/2 x squared plus c on the other side. So I would multiply through by 2 to try to get that y by itself. So here we do something a little bit strange with our arithmetic. We have not yet used any initial conditions to decide what c is. So when we multiply the right side, that's going to become a negative x squared, but I'm not going to call it a plus 2c because c is some unknown constant. 2 times c is still an unknown constant. We'll just still leave it as c. We still don't know what it is yet because we haven't solved for our initial condition. Now here we can square root both sides, and we will correctly note that it could be either a positive or a negative square root of negative x squared plus c. Now what we get here, it cannot be both of these positive or negatives, but at this point in time we don't know until we get more information like an initial condition. So what we're going to see is, and I'm going to give you a couple of different initial conditions. So for one, let's say that we have an initial condition that's going to be, say, 0, and we'll say a positive 2. So in that case, we're going to say 2 is going to be equal to, and we're not really yet decided what that is. We're going to plug in 0 for the x, so that's going to be the square root of c. So to get c, we're going to square root both sides. We're going to lose that plus or minus. That's going to give us a 4 on this side. So now we're going to get that y is equal to, we're going to talk about this plus or minus in a moment, and I'm just going to write the 4 first, so it's 4 minus x squared. Now, because our initial condition had a y value that was positive, that determines that this must be a positive square root of 4 minus x squared. So visually on our slope field, our initial condition is at 0, 2. So we can see this is going to be some kind of a top half of a circle. It's a semicircle, and it's going to be the top half based on our initial condition. On the other hand, if our initial condition was a 0, negative 3, then we would say that negative 3 is equal to, we've got plus or minus the square root of negative x squared plus c. When we plug in, we put plugging in 0 for the x, so that's just going to be a 0. So we've got negative 3 is positive or negative square root of c. We're going to have to square both sides to figure out what c is. The negative and the negative 3 get squared out. The plus or minus gets squared out with the radical, and we're going to get c is 9. So we say y is, and for a moment we're going to ask the question, is it positive or negative? And we're going to write that as 9 minus x squared. And again, that initial condition is going to determine that this, in fact, must be the negative square root of 9 minus x squared. And that fits with, then, we're going to have to get this semicircle that's going to be in the bottom half. It's the negative square root of 9 minus x squared. Okay? All right, I think that's all I got here. Very good.